Okay, I think we'll get started. So today we're going to continue our discussion of valence bond theory, and we will talk about the complete bond description. And then we'll also develop a way to represent on a two-dimensional board the three-dimensional structure, which is called wedge dash structure. So we've got our Lewis structure, so we'll assume we've determined the Lewis structure. The first thing we want to do then is identify the hybridization on each of the elements. So we label this sp3 because we need three sources. We have four sources of electron density, and therefore the electronic geometry around the central atom here is tetrahedral. In order to get a tetrahedral geometry with the hybridization, we need an sp3 hybridized orbital. So sp3 hybridized means tetrahedral. Tetrahedral means sp3 hybridized. So this is tetrahedral electronic geometry. Now, these are all sp3. Because there's four sources of electron density around each of these. Now, I do want to offer a word of caution here, and you can check your own Gen Chem book. Some authors will not hybridize the peripheral atoms. And I prefer to go with the hybridization because you want to apply Vesper theory to all of the elements, not necessarily just the central atom, in which case Vesper says those should be as far apart as possible, which would be tetrahedral, and you would need hybridization to get that. So I go with the hybridization of the peripheral atoms. When it comes to chemistry, it doesn't often matter too much. So if your book doesn't, that's why the author has sort of chosen not to do that. H does not hybridize, so that's just S. So it's it's S because H doesn't have any P's. It's a row 1, there are no 1p orbitals. So we've correctly identified all the hybridization around these. Now, to give the complete bond description, we would go like this. We would go CH colon sp3s overlap. Okay? Because an sp3 is overlapping with an S. Let's draw that actually. So I've got an sp3 and the S. And we're forming a sigma bond. So an sp3s overlap, sigma bond. Okay. And then we will go CCl, and we only need to do this once because of the symmetry here. And so we would say this is an sp3 overlap, sigma bond. Why sigma bond? Let's draw that. Here's our carbon, here's our chlorine. We have overlap in between, and so that it is a sigma bond. Okay, so that's the complete bond description of this molecule. Now we want to represent this 3D structure. This Lewis structure here is just showing the connectivity. We want to give that 3D structure, and that is called wedge dash diagram or wedge dash structure. And there's two ways to do tetrahedral. And what way you do is sometimes dictated by what molecule you have. I'm going to draw both ways, and then I'll kind of explain that a little bit more. So one way to represent tetrahedral is like this. And what does it mean? we draw just a straight line to represent bonds that are in the plane of the board. We draw a wedge coming out, so triangle here, coming out of the board. So that means the chlorine is coming out, kind of down and away here in this case. And the back here, the chlorine with the dashed is going back into the board. So back into the board. So dashes go back behind the page and wedges go out in front of the page. This is so let's look at this now. In 3D space, that would look like this. So I've got these two bonds, okay, in the plane of the board, this one coming out at you, and then this one going out, coming back at me. So this is the orientation that we are representing with this wedge dash diagram. Now, we could also do this. This would be a, oh, sorry, this is a, sorry, for our molecule, that's an H up there. We could, since this has this asymmetry here with this H, we can also draw it like this. Which is more of a pyramidal structure. And there, it's as if you're setting it on the table like this. And so I would set it on the table, and I would have one coming out at you, and two coming away, and one going straight up. So that is what's being represented here by this picture. And that's called the wedge dash diagram. So with the wedge dash diagram and then the complete bond description, we have the full-blown valence bond theory for this molecule. This happens to be chloroform. So we have the complete bond description and the 3D structure represented on a sheet of paper via valence bond theory. Okay, let's do a couple of other examples. So let's say we have this structure here, and I've cheated a little bit. I've already indicated a little geometry with the Lewis structure. Again, the Lewis structure says nothing about geometry, just connectivity. But it turns out this will capture the geometry here. So, forgot some important lone pairs here. So let's get the central atom. 3 sources of electron density. So that's going to be an sp2. So again, 3 sources of electron density, boom, automatically trigonal planar, and boom, automatically sp2 hybridized. Just boom, boom, boom. You can get that right away. So sp2 hybridized means trigonal planar around that atom, whatever's hybridized that way. And trigonal planar around a particular atom means sp2 hybridized. So sp2 here, 3 sources of electron density here, sp2. 4 sources of electron density here, sp3, sp3. Okay. This is going to lie in the plane. So this is the wedge dash structure for this molecule. There are no wedges, there are no dashes. It's still the wedge dash structure. Just everything lies in the plane. And if everything lies in the plane, the best way to draw that on a sheet of paper is to put all the bonds in the plane. Okay, so there's our wedge dash structure. Let's do the complete bond description. So CO is going to be, well, how does this work now? We've got this hybridization here, and then the oxygen has its hybridization coming down, and these will overlap. to form an sp2 sigma bond. But there is also the pi sticking out, sorry, the p orbital sticking out of both the carbon and the oxygen. So we have two adjacent p orbitals. Two adjacent p orbitals, and they'll overlap pink to pink and purple to purple, or plus plus minus minus. And so we will get a py overlap. I shorthanded this. This is fine if you write it like this. Let's be more explicit. This overlap, and that results then in a sigma bond. And then this is py overlap, and that results in a pi bond. And together they form the double bond. So a double bond is a sigma bond and a pi bond. And now we can see, back when we were talking about properties of bonds, that the bond order is sublinear in strength, meaning a double bond is not twice as strong as two single bonds. So it's not twice as strong as a single bond. And that is because we have a sigma bond and a pi bond is weaker than a sigma bond. A single bond is always a sigma bond. So the sigma bond and a pi bond is not as strong as two sigma bonds, but they're never two sigma bonds. It's a sigma bond and then pi bond. And so we see that we can understand now why the double bond is weaker than twice a single bond. Because it's composed of a sigma bond and a pi bond. Okay, now what else do we have? We have CF. This is going to be an sp2 sp3 overlap. And that is going to form a sigma bond. And there we have it. We have the complete bond description of this molecule, and this is its wedge dash formula. So if you can do this, then you've got that completely understood to the level of valence bond theory. All right, let's look at a sequence here of molecules called ethane, ethene, and ethine. And they simply differ by, is there a single bond, double bond, or triple bond between the two carbons? And so let's see if we can give the complete bond description here of ethane. Well, let's identify this. That's going to be an sp3. sp3 over here. And then all the hydrogens are going to be S's. So the complete bond description here is going to be carbon-carbon, sp3 overlap. And what kind of bond there? A sigma bond. And then the carbon hydrogens all are going to be the same. That's going to be an sp3s overlap. And that is a sigma bond. Okay. So there's the complete description. Let's take a look at it in 3D space here. That's going to look like this, right? Actually, it'll look kind of like that. They'll want to stagger. Okay. So there's only sigma bonds here. Sigma bond here, and also a single bond, and then sigma bonds here with the S's. Okay. So that is the structure. Let's draw the wedge dash diagram, and let's draw it in this staggered format. So the wedge dash diagram will be C, we'll put those in a plane, and then we'll put this one in a plane and this one in a plane. And then if that's in the plane, then this has to be one coming out, one going back, one coming out, one going back. And so that is precisely this structure right here. Okay. All right, let's look at its partner here now, ethene. Okay, quick identification, sp2, sp2, and these are S's here. So let's draw the wedge dash diagram. sp2, boom, right away. Trigonal planar. So we're going to go trigonal planar around this carbon, trigonal planar around that carbon, then everything's going to lie in a plane. And so this is the wedge dash structure. Even though there's no wedges or dashes, everything's lying in this plane. Let's give the complete bond description. That will be C will be an sp2, sp2 overlap, sigma bond, a py, actually it could be x or y. Let's call that x. Let's just say x here. Oh no, sorry, py has to be where, based on what we did earlier. Again, you're kind of free to do whatever you want there, but we decided to add a pz and a px, so that leaves the py free. Pi bond. And then the hydrogens, carbon hydrogen, is going to be an sp2s overlap, which is going to be a sigma bond. Okay, let's take a look at this structure. So here's how it's drawn on the board. All sigma bonds here between the carbon and the hydrogen, a sigma bond between the two carbons, and then above and below that sigma bond is the pi bond, coming from the overlap of the p orbitals. All right, last one. Let's do ethine. Okay, this is linear because it's two sources of electron density. And I should have mentioned this again here and here. Double bonds, triple bonds, they count as one thing because they're stuck together. They're one source of electron density. So that's going to be an sp, this is an s, and an s. Okay, so we've got our hybridization linear. Draw the wedge dash diagram. Well, again, they're all going to lie in a plane. In fact, they all lie in a line. Complete bond description. C is going to be sp overlap to give a sigma bond. We're going to have a px overlap to give a pi bond, and a py overlap to give a pi bond. So this triple bond, and all triple bonds are all triple bonds we're going to run into are sigma bond and two pi bonds. And so again, we know that from earlier, the bond strength of a triple bond is not 3 times, it's less than 3 times the bond strength of a single bond. Then the CH's is an SPS overlap, and that's a sigma bond. Let's take a look at that. That's this guy right here. So bring that out for you. and kind of look inside here. There's the sigma bond, sp overlap. Sigma bonds out to the hydrogens. And then we have those two available p's, the px and the py, and we create a double bond coming out at you, and then a pi bond coming out at you, and a pi bond up above and below. And that's how we can get two pi bonds, and then we always only have just one sigma bond. Okay, so I'll kind of rotate that slowly so you can see that. Okay, well, let's do this is a pretty fun one here, this guy. If you can do this one, then you're in really great shape. So maybe I'll challenge you if you want to pause the video and see if you do this, see if you can get this and to the point where you can get the right wedge dash diagram. Okay. All right, so hopefully if you did decide to pause the video, you've got an answer here. Let's see how that goes. See if you got the complete bond description. So let's identify things. This is an sp2, sp, sp2. How do we see that? Three sources of electron density, boom, automatically sp2. Two sources of electron density, boom, automatically sp. Three sources of electron density, boom, automatically sp2. Hydrogens are all S's. Okay. Now let's start to give the complete bond description here. So I'm gonna call this A and B over here. So C to CA, okay, is going to be sp2 sp. We've done this enough now. I'm going to stop writing the word overlap, and I'm just going to write here now sigma bond. Now, this is going to have, because this is sp2, it's going to have one leftover p. So let's call that px, because the pz has been used up. So let's call that px. This guy has both its px and its py free, so its px can overlap. We can never get a px py overlap because they're orthogonal. So px px pi bond. And so that's a double bond. That's the double bond we see there. So now let's look at CB. So that's this guy to this guy. That's going to be an SP. Oh, sorry, I've got this wrong. The way I wrote it here, SP, SP2, sorry about that. The way I wrote this here, that's going to be an SP, SP2 sigma bond. Okay. Now, how do we make the double bond? Well, I have used up this px to create this double bond, but I still have a py here. This guy has a py, but it's rotated, right, relative to this. So that's going to be a py pi bond. And then finally, CH is going to be an SP, so A or B, right, is going to be a sp2s sigma bond. Okay, so now we got to write the wedge dash diagram. And again, let's put a little coordinate system up here. So let's call this Z, right? Because the interbond axis, we always want that to be Z, and this will be X going in the board, and then Y will be coming out at us. So we've decided this first one, this A, is creating the pi bond in the X direction. So that's going to look like this. Because we've decided the X lies in the plane here. The Z is always this sort of interbond axis. So that's going to be C over here, right? But now this one has to be rotated. So this is going to be like that, not in the plane. So this is not a planar molecule, and we have to know the complete bond description in order to get that right. So again, if you got this right, then you've really got your got things down. If you didn't get it right, then just keep practicing and keep thinking about it. Really try to tell yourself the story of this molecule. It's key to it's a really good test, I guess not key, but a really good test of, do you know valence bond theory? Well, let's look at it in 3D. I think that's helpful. So I'm going to orient it exactly how we did here. So just like that, and then I'll bring it out towards you. This model's a little more compacted, so a little harder to see. But notice here now that, oh goodness, let's see. I mislabeled things. Let me start over. So we've decided up here, that's a px, and we've decided our x is up here. So C, so that means our sp orbital here, sp2 orbital, is the z and the y. So that's going to be like that. Got my axes turned around. And then this will be like this, because what's left over, the double bond is in the y direction. That's coming out at us. So that means this has to be twisted so that this is in the plane. All right, let's again take a look at the 3D structure now with this x and y. So I'm going to put this like this, and now I'm going to bring it up here. So if we're calling this the y direction, this the x direction, here is our px overlap right here, and then coming out at us is our py overlap. And so I'll just rotate this slowly like that. Okay. All right, so this is a really challenging molecule, and easy to get, as you saw here, easy to get your axes flipped around. But in the end, I mean, you still get it right. You get that it's twisted, even if you do get your axes flipped around. But if you want to match with what we wrote up here, then we would need to draw it this way on the board. Now, of course, totally, you could have called that py and this px, and you would have drawn it the way we did earlier, the mistake I made earlier, and that would have been fine too, totally fine. So there's whatever you drew, if you practice this ahead of time, if you had it the way I had it, or if you had it this way, then both are correct, right? They're just rotated well relative to each other. All right, so that is valence bond theory, complete bond description. And so that kind of completes the story on valence bond theory. So keep practicing this. And like I say, this is even practicing professional inorganic and organic chemists use this all the time.